Hi, welcome to lesson 1.2 from Foundations of Math 11. We're going to talk about proportional thinking and specifically demonstrate the ability to understand and work with similar figures and scale factors. So we're going to start by talking about similar figures and scale factor. When you make a copy of something, you want it to look exactly like the original. It has to have the same shape, the angles need to be the same, corresponding leg lengths need to be proportional, and we'll talk a bit about that more later. We call these similar figures. And we use this symbol, it's called a tilde, a little squiggly line, to indicate that figures are similar. So for example, I'm going to draw a triangle here that's got a right angle in one corner, and it's got an angle of certain size in that corner and an angle of a different size in this corner. And then I will draw a smaller version of the same triangle within the limits of my drawing ability. But I'll use symbols to tell you that this angle up here is the same size as the red angle in the original one, and this angle is the same size as well. And these figures are similar. Okay, so we use that symbol, tilde, to show that those two figures are similar. So to recap, two figures are similar if corresponding angles are the same and corresponding sides are proportional. Now we're going to talk about scale factor. Scale factor is a number that tells us how much bigger or smaller something is compared to the original. The formula, or the equation, is scale factor equals original. The formula for scale factor is scale factor equals image length over original length. And I will hound you to write that down. Scale equals image over actual. Some people do it equals copy over original, or image over original. You can pick what you want as long as you're writing one of them. I don't like the original because it looks like a zero, so I try and avoid that. Okay, so let's fill in this table. If the image is larger than the original, the scale factor is going to be greater than 1 because our image size is greater than the original size, and that when you reduce that to a decimal, it's bigger than 1. And the image in that case is an enlargement. If the image is less than the original, the scale factor is less than 1, and it's called a reduction. If the image is exactly the same size as the original, the scale factor is equal to 1, and it's neither a reduction nor an enlargement, it's an exact copy. All right, let's do some calculations. This Chinook salmon is actually, there's a typo there. Actually, I've used these notes like 17 times and never noticed that. It's actually 46 centimeters long. What is the scale factor of this drawing? Well, I can't measure it on the screen because it's going to be a different size, but I'm going to tell you that it is 6 centimeters. There will be questions where you actually need to get a ruler out and measure it on your paper. Okay, so scale factor or scale, because the formula is the same. Scale factor equals image over actual. Plug in my numbers, it's 6 centimeters, and the actual size was 46 centimeters. Now, it's critical that these two numbers have the same, they must have same units. okay? Because what happens now is I get my calculator out and I go 6 divided by 46 and I get 0.13. And because the units were the same up top, the scale factor has no units. No units. It's just a number, okay? So this has got a scale factor of 0.13, which means it's smaller than the original. It's a reduction from the original. Okay? Example 2. Or no, now we're going to talk about scale versus scale factor. Now I'm going to be honest with you, this is something that textbooks get wrong, and it kind of drives me crazy. A scale factor is a number. It doesn't have any units. It's usually written as a decimal, like 0.025. It can be written as a fraction, which would be, for example, 1/4. Okay, or you can think of that as a ratio, 1/4 as a ratio. But there's no units, okay? Scale isn't done as a fraction, or sorry, as a decimal, it's a ratio or a fraction. So for example, I can write it as a ratio of, this would be a different one, but 1 centimeter to 2 meters. Or I could write that as 1 centimeter over 2 meters. So what it means is that 1 centimeter on your scale drawing, for example, equals 2 meters on your actual item, okay? And the formula is the same. Scale equals image over actual, or scale equals image to actual. Either way, the order matters, and it's image first and then actual. Okay, let's do some examples and do an example comparing scale and scale factor. Okay. The flying distance from Dawson City to someplace in the Yukon is 180 kilometers. Calculate both the scale in centimeters and kilometers and the scale factor for the diagram. So I'm going to do scale first. So scale equals image over actual, which is 1 centimeter is 180 kilometers. Or I can write that as 1 centimeter to 180 kilometers. Okay, that's the scale, and I'm done. That was really easy in this case, okay, because the scale you can have different units. If I wanted to do this, if I'm doing the scale factor for this situation, scale factor, and this is a great example of where you would not use scale factor, but let's go ahead and do it so you can see the difference. Scale factor is still image over actual, and our image is 1 centimeter and our actual distance is 180 kilometers. So it starts off the same, but we need the same units. So I'm going to take this information, I'm going to go over to the side of my page. I call this my back of my envelope calculations, where I need to change those to the same units. Now, I don't want to write centimeters as some decimal of a kilometer because that's just really ugly, and we work better with whole numbers and integers than we do with decimals. So I'm going to change my 180 kilometers to be some number of centimeters. Okay, so using the techniques we did in the last section, 1 kilometer is 100,000 centimeters. So 180 kilometers is going to be x centimeters. And then I'm going to figure out my x is going to be 180 times 100,000 divided by 1. X equals 18 million centimeters. Okay, so I'm going to take this number and I'm going to punt it back over here so that my scale factor now is still image over actual, and my image is 1 centimeter to 18 million centimeters. So my scale factor is 1 over 18 million if I want to do it as a fraction, or if I change it to a decimal, it's 1, 1, 2, 3, 4, 5, 6, 7 with 7 zeros. 1, 2, 3, 4, 5, 6, 7, and 5, 6. So that's my scale factor. Okay. Now, the thing with scale factor is that because the units don't matter, okay? So with scale factor, units don't matter. So, for example, 1 centimeter on the map represents 18 million centimeters on the ground, in this case. 1 millimeter on the map equals 18 million millimeters on the ground. And I could measure things in pencil lengths. So 1 pencil length on the map equals 18 million pencil lengths on the ground. Okay, and that's in comparison to the scale, where the scale is specifically 1 centimeter on the map is 180 kilometers on the ground. So when the numbers are hugely different like this, like maps, scale makes much more sense than scale factor. There are other contexts where scale factor makes more sense, and that's when the numbers are closer together and context driven. Okay, so that's the lesson for 1.2a. Go ahead and do the assignment, the practice work, and check your answers and do your corrections, and then come on back and we'll do lesson 1.2b.